If you've ever played a contact sport or chased after a friend, then you have unknowingly followed a pursuit curve. The act of pursuit has been occurring since the beginning of the human race. I can imagine that even our Neanderthal ancestors pursuing their game followed a pursuit curve. However, mathematical description was not possible for this until the invention of calculus in the 1600s. The formal definition of a pursuit curve is the path followed by a particle, called a pursuer, that is trying to pursue another particle. Examples of pursuit curves include the predator-prey pair, a Coast Guard boat pursuing a hostile ship, and space station boarding trajectories. We will dive into a very fun, old, and interesting problem that appeared in a book in the early 17th century. In 1638, an author by the name of Francis Goodwin published The Man in the Moon. In this story, an astronaut harnesses 25 swans to himself and flies to the moon based on the knowledge that swans follow the moon during their annual migration. If the swans fly at a constant rate, the trajectory they form is not a straight line, but a pursuit curve. To model this celestial problem, we will position Earth at the origin O. We will take the moon's orbit around the Earth to be a counterclockwise circle with a period of 27.3 days and a radius of 1 lunar unit, which is the distance between the Earth and the moon, assuming they're point particles. And since this problem does not involve the sun, we chose to use its sidereal period of 27.3 days, which depends on the fixed background of the stars, or just that its period is the time it takes to return to the same point around the Earth. Some clear and obvious assumptions we're making for this problem include the lack of gravitational forces on the swans fly considerably faster than they physically are able to, and the harness and swans are indestructible.
Okay, now setting aside the swan to the moon problem for a second, let's take a look at the general form for pursuit curves. Okay, assume we have a point A that's defined by the position vector A vector. And we have a point B that's pursuing point A that's defined by its position vector. Okay, now since we know that point B is always traveling towards point A, we know that the velocity vector is always in the same direction as A vector minus B vector, or the difference in position vectors. So if we divide the velocity vector by its magnitude, and we divide this vector by its magnitude, we end up with two vectors of length 1 in the same direction, which basically means they're the same vector, so we can set them equal to each other. Okay, so we do that here. We have b vector prime divided by its magnitude, a vector minus b vector divided by its magnitude, set them equal to each other. And that's going to be our basic setup for the rest of this derivation. Okay, so the rest is basically algebra. We're going to multiply this term on both sides, and it becomes this. And this term it doesn't have any vectors in it, so it's going to be the same in all components of the rest of the vectors. So we see that when we take it into component form, we can go from b vector prime to bx by prime. And then equals this term times the components for this vector value, which is ax minus bx, ay minus by. Okay. Now we can rewrite this in the form of two equations instead of one vector value equation. So we can take bx prime equals this term times ax minus bx, which is where we get this equation from, the top one. And the second equation is by prime equals the same term times ay minus by, which is where we get this equation from. So now we basically have a system of first-order differential equations that can be plugged into a computer software and solved for. Okay, so we have the general form for the pursuit curve here, and we're going to make a specific example of it using the swan to the moon problem. So in order to use these equations to model the pursuit curve of the swans, we're going to have to make a few assumptions. The first one is that the Earth and the moon are basically point particles, so we can define the initial condition of the swans to be at the origin. So the initial position of the swans would be at x equals 0, y equals 0. So the next assumption we make is that the moon's orbit is a perfect circle, and if we assume that, we can model the moon's orbit using these parametric equations. So the x position of the moon is r sub m cosine of 2 pi t, and 2 pi is the angular frequency, and you can define it to be 2 pi so that for all integer values of t, the moon will be at this point. So t equals 0, or you get cosine of 0, which is which equals 1. So x of moon is r sub m, and r sub m is the orbital radius of the moon. And another assumption that we can make is that the swans are not being acted upon gravitationally by the Earth or the moon. And another thing we have to use for the final equation is that the velocity of the swans is some constant of times the velocity of the moon. And as you'll see in the maple video coming up, you'll see that this value of k becomes important around the value of 1. So k at the value for k, or k equals 1, the behavior of the pursuit curve changes.
Based on the speed ratio assumption, the solutions have different behaviors. There are 3 possibilities for the speed ratio parameter, and this solution shows the case that the swans are traveling at a slower speed than the moon. Therefore, the speed ratio value is greater than 0 and less than 1. This specific graph shows the case that it is equal to 0.5. The outer circle seen on the graph is the orbit of the moon. The swan's path asymptotically approaches a circular orbit around the Earth that is slightly off-center according to the starting position of the moon. As time approaches infinity, the center of the swan's orbit gets closer and closer to Earth's position. This holds true for all solutions in which the swan's speed is less than the moon's. However, it is important to note that as the swan's speed approaches the moon's speed, the radius of the swan's orbit in the solution also increases proportionally until it reaches the radius of the moon's orbit.
Regarding the specifics of the maple file you're looking at, the first few lines mention x moon and y moon. These are the parametric equations for the motion of the moon. The next line after that defines a variable called speed ratio. This is the constant value k that we mentioned back in the derivation, which is the ratio of the swan's speed over the moon's orbital speed. The line labeled ODE cis defines the final system of first-order differential equations that we use to solve for the pursuit curve, which are the final equations listed from the general derivation you saw earlier. The line starting with swan plot uses the DE plot command and the initial position of the swans to solve for x of t and y of t, which are the final parametric equations for the position of the swans as a function of time. The pursuit curve is graphed and animated at the bottom, along with a circle for the moon's orbit.
This next solution examines the possibility that the swan's speed is equal to the moon's speed. This means that the speed ratio parameter is equal to 1. Since the swan's orbital radius is proportional to the speed ratio, the swan's orbital radius is equal to the moon's orbital radius. As seen here, since both the swans and the moon travel at the same speed, the swans never reach the moon. Instead, they follow behind it on its orbit. The last type of solution is shown here. Solutions that have this kind of path exist when the swans are traveling at a speed that is faster than the moon's speed. Therefore, the speed ratio parameter is greater than 1. This graph shows the specific path taken by the swans, and the speed ratio is set equal to 1.5. This solution is different than the other two in a couple of ways. First, since the swans are traveling faster than the moon, they actually reach the moon this time, instead of following it forever. Also, the swan's path does not become a circular orbit around the Earth, as in the other cases. The swans instead follow a path that spirals out away from the Earth. This happens until the swan's distance from the Earth is equal to the moon's distance from the Earth. When this happens, the swans have reached the moon and have also reached the end of their pursuit curve.
So in conclusion, the swans reach the moon only for values of speed ratio greater than 1. However, the moon's actual orbital speed is upwards of 2200 miles an hour. So in order for speed ratio to reach a value greater than 1, the swans will have to achieve a speed greater than that. I think we can all agree that this isn't practical or possible. If we use a reasonable value for the average speed of a swan, let's say 30 miles an hour, the value for speed ratio becomes 0.0136. It turns out that this value of speed ratio causes the radius of the swan's smaller pursuit orbit to be less than the Earth's radius, so that the swans would be continuously hitting the ground if they actually tried to follow the moon as it goes below the horizon.